name is Luigi Iapichino from the Leibniz Supercomputing Center. And together with Fabio Baruffa at Intel, I made first exploration of the performance of quantum computer simulators on HPC systems. So don't worry about the details about the physics of quantum computing simulators. I will try to give just an HPC overview on these. Just a few words about myself. I'm an application specialist at the Leibniz Supercomputing Center. I started working since about 1 year ago on the field of quantum computing. I'm the co-founder of a discussion platform called Bavarian Quantum Computing Exchange on this topic. And this project has been funded by Intel, is jointly done by LLZ and Intel, and as I said, developed together with Fabio. I will give the following structure to my talk. I will try to convince you why simulations for quantum computing are important and why these are needed on HPC systems. I will go on describing the Intel Quantum Simulator, an open source tool by Intel for doing such simulations. And I will try to guide you on a few ideas on quantum computing and performance considerations on these tools. So I will introduce just the details which are really necessary to understand what's going on in terms of HPC performance. Then I will show you the first profiling of the tools, the first performance results that we have, and I will describe where we want to go from here. Why quantum computing simulators? Well, the point is that right now there is no available hardware which is available for the users. There are a few systems which are available for the vendors, a few systems which are available through a cloud, but most of them are so-called noisy and intermediate scale systems, so that it's very difficult for users to test and develop on these systems their algorithms, because they are basically so noisy that they allow just very small studies. So in many fields of IT, using simulations is a very valuable tool. And so it is also in quantum computing, because using a simulator, one can evaluate the complexity of a circuit, one can study algorithms that otherwise would not be possible to be modeled analytically, and one can even simulate what is the noise that would affect these algorithms on a real system. And in many cases, this can be a first entry point into quantum computing. Why we need HPC systems for this? These kind of simulations are twice very demanding. On the one side, the size of the quantum state that one wants to simulate grows exponentially with the number of qubits, so with the size of the system, the quantum system that one wants to simulate. And on the other side, the complexity of an algorithm translates, of course, in another constraint on the simulation time. So both for memory and simulation time, a solution is to run on HPC resources. So let's talk about the Intel Quantum Simulator, IQS. This is an open source simulator of quantum circuits designed for running on HPC systems. Is currently developed by Justin Ogabon, Giangiacomo Guerreschi, and Fabio Baruffa at Intel, and it can simulate single qubit gates and 2-qubit control gates. So the gate are basically the operations which are done on the system. Very roughly. So this is written in C++. It has a hybrid parallelization MPI plus OpenMP. There is the GitHub repository for this. There is a paper that you can have a look where everything is described. So just the very few basic things about the gates, so the operations that one can perform on an algorithm. and about the representation of a system, so of the quantum state. So just to understand why the problem is complex. So when you have a system with n qubits, basically the state of this system is represented by 2 to the n components. So in the case of phi, as you can see here, we have these coefficients, so alpha 000 to alpha 111. So these are 2 to the nth component in a case of a system n qubits that completely represents the system, and these are complex numbers. Of course, one needs to store in memory such state, and depending on the size of the state, probably this needs to be stored across multiple computing nodes, and MPI communication is needed in this case. And a qubit is basically represented by a unitary matrix. So, sorry, not a qubit, a gate is represented by a unitary matrix. So basically every gate acting on a single qubit is identified by 4 numbers. So in the simplest case that we can have to visualize everything. So we have, assume a system of 2 qubits. System of qubits can be represented in this way with 4 amplitudes, alpha 00 to alpha 11, that can be represented as a vector, for example. And every time we act with a gate on the system, so we apply a gate to a precise qubit, but indeed the general formula, which is shown here on the left-hand side, shows that every single amplitude in the system is affected by the gate, even if this gate applies to a single qubit. This is, of course, a consequence of the fact that the qubits are entangled to each other. This is a typical concept of quantum computing. We don't go into this detail, but it's enough for you to see that basically every gate modifies the state of every amplitude. And an interesting property that we can see already here. So here we apply the gate to qubit 0. And when we see how it modifies the amplitudes, we can see that the coefficients of the gate appear, and also the amplitudes alpha 00 and 01, which in memory are stored in a consecutive way. So this brings us to a more general idea. So how a gate acting on qubit k acts, which is very well represented by this plot here on the left-hand side. So if we act on qubit 0, we have what happens here, namely a gate which applies to elements with stride 1. So always on consecutive elements, as we have just seen in the previous slide. If we go to a gate acting on on qubit 1, in this case, we do see, applying the formula that we have seen in the previous slide, that there is always a stride, in this case, a stride 2. In general, in a system with n qubits, if we apply a gate on qubit k, we access the element with stride 2 to the k. So this is a very important feature to understand the performance of IQS. This means that if we apply a gate on a low qubit, we access with a small stride, and basically we access amplitudes which most likely reside on the same node. If we have a gate acting on a large qubit on the system, probably we access amplitudes which reside on different nodes, and then MPI communication is needed to this gate to be operated. So from a viewpoint of performance, IQS is a data-intensive application and also memory-bound. We have that the memory footprint of the state grows as 2 to the n plus 4, where the 4, well, if we are working with floating numbers, and every amplitude is a complex number. So here comes the 4 into the game. The performance of every gate operation on qubit K depends on N and on K for the reason that I've just explained. And when we talk about simple gates, simple operation, basically all we need to determine the performance is the DRAM bandwidth or the network bandwidth if we go through the network of bit internode communication. And just to provide an example of this statement, IQS is the first application where I could see a clear change in performance on the Intel Xeon Phi on the Knight's Landing when allocating the memory on the MCD-RAM, on the DRAM, and the performance difference was close to the theoretical expectation because of the different bandwidths of these two memory elements. Of course, working on KNL has mostly didactical motivations right now, but it shows already that the DRAM is very important in this case. Well, what is the scope of the profiling work that I want to show? So I said that right now we know how Intel QS performs on simple operations. We want to test these on more complicated algorithms. We know something already about the features of the code. We know that it has a strong focus on efficiency on modern architectures because it's been written by people knowing about these details. We know that optimizations I have already implemented in the design stage for this application, like vectorization via SIGD-pragmas, threading optimization is there, cache blocking is there, MKL library is used throughout the application very intensively. Despite of that, so far, most of the attention in the performance has been taken especially for simple gates, but for more complicated algorithm, we want to see a bit better on a complex case. And we want to probe mainly the MPI layer of the code because for OpenMP there are complementary projects going on already on their own. Our target system is at the moment SuperMUC-NG, which is the high-end system at the Leibniz Supercomputing Center, number 10 on the last top 500 non-accelerated system consisting of more than 6,000 Intel Xeon Skylake nodes. So on this system, we have already some performance results at scale, which comes from the IQS method paper, where also this plot come from. We can see that the code is very well behaving both on strong scaling and weak scaling on simulation of single qubit random gates. So these are simple algorithms, as I said, not complex case, but still gives already a good indication that the code is well behaving, that the strong scaling behaves as expected, lowering with the number of MPI processes. So the effects on the right-hand side of the plot are given by the fact that from these values on, we go from internode to intranode communication, and then there is a jump in the execution time. Same thing for the weak scaling. Here, simply if we see the plots overlapping to each other, this means that the performance is good, that the scaling is very good, and we could check on this system up to 1/3 of the system, quantum problems up to 42 qubits, which is a good result. Now, for a more complicated test case, we go back to single node profiling. We want to test the quantum Fourier transform, which is basically the quantum analog of the inverse discrete Fourier transform. This is a non-trivial test. This is part of many important quantum algorithms like the Shor's factorization, which is a crucial important for quantum cryptography. We run on a single node, on a single Skylake node, a system of 29 qubits, where the memory for the quantum state is 8 gigabytes. On the test, which has been done, both single precision and double precision quantum QFT are executed. As I said, yeah, Intel Xeon scalable processor Platinum. That's the one of SuperMUC NG. We work with compiler tools from Intel Parallel Studio 2019, and we focus on MPI scalability and performance because the OpenMP layer is on the code, but is followed by different projects. Now, about the MPI scaling, yeah, we can see that at the beginning, this is not satisfactory. So this is scaling on the node. The last point is hyperthreading. The dashed line is the ideal scaling. As we go beyond a socket, well, even before, we can see that there is a bottleneck here. Which is relieved by the hybrid parallelization somewhat, but yeah, we basically move the MPI bottleneck into some OpenMP issue somehow. So we see also a bottleneck on memory and cache stalls, as I would expect from a code which is memory bound. There are good news. So the vectorization is very good. So about APS, the application performance snapshot, told us that about 90% of the instructions are vector instructions. However, nearly all of them are AVX512 instructions, and even forcing by compiler option the use of the ZMM register does not have level performance from this viewpoint. And yeah, because of the severe memory bottleneck, although the number of vector instructions is rather large, the performance gain due to vectorization is just 1.25x, which has been measured comparing the vectorized version of the code with the code version compiled for with minus novec minus nosimd for having the scalar performance. I have run the Intel Advisor on IQS. So this is a plot of the roofline. I could see that 90% of runtime is spent on MKL instructions, which is very good. 60% of the runtime is spent is vector instructions. Somehow there is something that needs to be investigated here because the top 5 vectorized loop use only SSE, SSE2, and AVX instructions. So as I said, there is something on the vectorization side that has been should be explored, as in many other viewpoints. This is just the initial assessment of performance. We see good arguments, good signs that one can go deep and reach good performance, but at the beginning there is obviously some work that needs to be done. The roofline plot shows that the code is basically DRAM bound, so this line is the DRAM bandwidth and all the points are below this line, so the code is DRAM bound as already anticipated by APS. And with it, I am at my summary. Quantum computing is a field which has a really growing momentum at the moment. You can see these in press release and news very often. However, there are still some hurdles, especially in terms of accessing the hardware for researchers. And we showed that quantum computing simulators like IQS can help into this, can be used for exploring, testing, and implementing the quantum algorithms, making use of HPC resources which are there. So we don't need to wait for HPC resources as we need for quantum resources. We can use what we have now to simulate already quantum systems of relatively large size. This application is being developed keeping HPC performance in mind, which is good, and it's not very common in the communities. Simple gates perform well, scale well. For more complex algorithms, there is work to be done and room for improvement. And for the future, of course, we need to prepare this code for a coming system, for upcoming programming models. It's clear. So now it's been run on an unaccelerated system. We need to prepare this for a coming system that most likely will be accelerated. And I assume that quantum computing on 3 exascale machine has a potential, which in my opinion is comparable with the one of the current noisy hardware. And with it, I end my call. So thank you very much for your attention. Will be interesting what will happen for questions, because I cannot hear you, unfortunately. And this is the first time it happens to me to have such a talk in front of. Okay, I see already on Q&A one contribution.
There is a question, what is gate fusion, David?
So I see one question. What is gate fusion? So with gate fusion, basically we indicate, well, it's better described in the method paper, but basically there are some ways for performance of working on more gates together, just to better operate on data which are already in cache, for example, and there are ways to optimize these gates and having them fuse to each other. So this is in short the
David, does this answer your question?
to that.
David?
I will stop sharing my screen now.
Yeah, it answered my the question.
Okay.
Thank you.